Welcome, physicists. This is the concluding part 4 of the chapter Light, Reflection and Reflection that we were doing. In the last part, we did up to the sign convention of concave and convex lenses. Now, we'll take the case of image formation in convex lens. As you know that convex lens is a converging lens. And remember one thing, that as the object is far away from the lens, the image will be nearer to the lens. And as the object starts moving closer to the lens, the image moves further away from the lens. That means if the object is far, image will be near the lens, and if the object is near, the image will be far. The case 1, object is placed at infinity, the image is at focus. It's real and inverted and highly diminished. If the object is kept beyond 2f, 2f corresponds to center of curvature in the case of spherical mirrors, then the image will move away from the focus and will be found between f2 and 2f2, real, inverted, diminished. If the object is placed at 2f1, then the image will be at 2f2, real, inverted and same size. If the object moves further closer, that is between f1 and 2f1, the image moves beyond 2f2 and real, inverted and enlarged. When the object is placed as 2f1, at that point, the image and object are equal. If the object is beyond 2f1, image will be diminished, and if the object is between f1 and f2 and 2f2, then the image will be enlarged. Now, if object moves further closer and comes at focus, the image goes at infinity. This is the inverse case of first. Object at infinity, image at focus. Object at focus, image at infinity. Highly enlarged, real and inverted. Now, if the object is moved further closer between focus and the optical center, then the image will not be real. It will be formed on the same side of the lens and will be virtual, erect and enlarged. Now, coming at the ray diagrams, case 1, this is the case 1 of object at infinity, image at focus. Object beyond 2f1, images between f1, f2 and 2f2. Object at 2f1, image at 2f2. Both are at the same distance from the optical center and the size of the image and object are equal. Object moves further closer between 2f1 and f1. Image moves further beyond 2f2. Now, the image size will start increasing as compared to the object. When the object is at focus, image form will be at infinity, real, inverted and highly enlarged. And if the object moves further closer, that is between focus and optical center, then the image is formed on the same side of the lens and it will be virtual, erect and enlarged. This is the particular case that is applicable when you are observing something very small through a magnifying mirror, magnifying glass. Now, coming to some applications of convex lenses: microscope, camera lens, projectors, flashlights, magnifying lens, telescope. And one very small convex lens is inside our eyes. That is the crystalline lens and also called the eye lens. That will be taken up in the chapter of human eye and the colorful world. Image formed in the concave lens. Concave lens is a diverging lens. And remember one thing always, that in case of concave lens, the image is always virtual, erect and diminished. There are two cases mentioned in your textbooks. When the object is at infinity, image is at focus, highly diminished, virtual and erect. And if the object is placed anywhere between infinity and the optical center, or the between anywhere in the lens, the image will be between focus and optical center, diminished, virtual and erect. Coming to the ray diagrams, these are the two cases of spherical mirror, concave spherical lens. Object at infinity, image, if we are observing from this side, the image will be formed at this point because this is the diverging case. Similarly, when the object is anywhere between infinity and optical center, then the image will be on the same side again. It will be small, virtual and erect. Applications of concave lenses. Concave lenses are used in the cat's eye, that is the peephole through the mirror, or the from where we see who is the visitor at the door. Used to correct myopia. Myopia is a defect of eye in which the near objects are clearly visible, but the objects that are far away are not clearly visible. For correcting those that type of defect, concave lenses are used in the spectacles. They are used in flashlights. Why? So they are of diverging nature. When the light passes through the lens, it gets diverged and a large area is illuminated. Also used in binoculars and telescopes. Now coming to the lens formula or the lens equation. Remember the mirror equation? 1 by f equals 1 by v plus 1 by u. Here almost the same, but the plus sign is replaced by a minus sign. Why? Because in case of spherical mirrors, the real image formed on the same side as the object, but in the case of lenses, the real image will be formed on the opposite side of the lens. So there is a slight change in the formula, where f is the focal length, v is the distance of image from the lens, and u is the distance of the object from the lens. Just like we had magnification in case of mirrors, we have magnification in the lens also. The same formula is there. Magnification is equal to height of image upon height of object, or v upon u. Magnification in case of mirrors was m is equal to minus v upon u, but here it will be v upon u. Here m is the magnification, hi is the height of image, and ho is the height of the object. Further, it can also be written as magnification is equal to f upon f plus u, or f minus v upon f. If you don't want to calculate the height of image and height of object, then magnification can also be found out like this. Suppose in the question, the height of object is not mentioned, only v and u are mentioned, then you can use this particular formula. Power. How strong is the lens? What does power mean? Power means how much a lens is capable of converging or diverging a parallel beam of light. If a convex lens diverges a parallel beam of light very close to itself, then it is a powerful lens. If it diverges a parallel beam of light farther away from itself, its power is less. Similarly, concave lenses also, if the divergence is more, power will be more. If the divergence is less, power will be less. How do we calculate this? P is equal to 1 upon F. Power is reciprocal of the focal length. If focal length is less, power will be more, and focal length is more, power will be less. But this formula is used when focal length is in meters. But if the focal length is in centimeters, like generally the numericals in the question paper are presented, then you can use P is equal to 100 upon F. In this formula, if you are using this formula, it is applicable only when the focal length is in centimeters. Now coming to a very important phenomenon, total internal reflection. What is total internal reflection? When it has certain conditions. First condition is that light must be traveling from a denser medium to a rarer medium. That is, from a medium of high refractive index to a medium of low refractive index. Let's suppose we will take 4 cases here. One, when the light is incident at the boundary perpendicular to it. Then in case of angle of incidence will be 0, so angle of refraction will also be 0. So the light will emerge straight. Now, the second case, light is incident obliquely. Now, the lower arrows, this shows that actually 2, 3, 4% of the light is reflected back, but most of the light is refracted outside. In this case, refraction will take place and the light will refract away from normal because light is traveling from a denser medium to a rarer medium. If we increase the angle of incidence further, the angle of refraction also increases. At a particular point, for a particular angle of incidence, the angle of refraction becomes 90 degrees. That means the refracted light will be traveling along the boundary between the two media. That particular angle of incidence for which the angle of refraction becomes 90 degrees is known as critical angle, theta c, critical angle. But if the angle is further increased, that means the angle of incidence is now more than critical angle, then the light will not be refracted, it will be reflected back into the same medium. This is called total internal reflection, and the formation of the rainbow that you will be studying about in human eye, the same phenomena will be applicable there. Now, this phenomenon of total internal reflection has some applications in our real life. First of all, everybody has heard about optical fiber, the fiber through which the internet service is coming into our homes. That is an optical fiber. It is based on total internal reflection of light. No matter how we bend it, if we curve it, we bend it, no problem. The light entering at a particular angle will suffer total internal reflection and will emerge from the other end, irrespective of how many bends are there. This light that is incident in this fiber, it carries the signals, and those signals are received by our router. This is a periscope. In this also, the phenomenon of total internal reflection is used, and this is a retroreflector. That means a light which is coming from a particular direction is internally reflected twice to go back into the same direction. That concludes our part 4 and the concludes of a chapter also. Revise this chapter well, and if you have any doubts, do notify us. Thank you for watching. Have a nice day and happy studying.